Hello everyone, today we'll talk about the problem first missing positive, today's LeetCode's daily. We're given an unsorted array nums, have to return the smallest positive integer that is not present anywhere in nums, in linear time and constant space. Now this problem is quite similar to two previous dailies, for which I have already recorded videos, so perhaps if you don't know how to solve this problem and you want some inspiration, you can look at one or two of those previous videos. Now here, since the ideas are similar, I will skip some of the explanation. And of course, the crucial observation or idea is that we can use this original array, modify it, and then this will actually allow us to use O of n space, with some limitations that we cannot destroy too much of this array or we cannot destroy it irreversibly. Well, in a sense, we can destroy it irreversibly, just in such a way that we can actually finish running our algorithm and give the correct answer. Okay, so since the numbers here can be arbitrary, they can range from int min to int max, there is probably no easy way to mark them in such a way that we can then restore the original array. But since we are not being asked to do so, we can do some destructive modifications. And the idea here will be, of course, to mark elements. And one thing to notice when it comes to the way we want to mark them is that possible answers to this question range from 1. Since 1 is the smallest positive integer, perhaps it is the smallest missing positive integer. It can be, of course, equal to n. In this case, it could be that 6 is the first missing integer. It could also be equal to 7. If what we're given is a permutation from 1 to n, then 7 in this case would be the missing number, but nothing above 7, and of course nothing below 0, is a correct candidate for an answer. So in the rest of the algorithm I will be using some x or something to mark an element that is not a possible candidate, which is out of bounds in this case. So let's transform our array first. 3 is an OK candidate, so is 4. -1 is not, so we'll just put an x here. 1 is OK, 4 is OK, 18 is not. And now if we had an auxiliary array of bools, that would tell us if we have already seen an element on this position, which of course originally we have not seen any elements, then we'll just mark that we have seen a 3, a 4, a 1, a 4. We'll be marking them, since we are using zero indexing, one element to the left. So when we see a 1, we'll mark position 0, when we see a 3, we'll mark position 2, and so on. And then we'll see that we have marked position 0, so 1 was present. We have not marked position 2, and so 2 is the answer to our question. And now the main problem, we have to use only constant auxiliary space. So there are two main ideas of how to do this. And the first one would be, of course, treating those elements as pointers into this array. We can just mark an element, we can make it negative the first time we see it. So in this case, we are going through the array, and now this 3 points to element of index 2, 3 minus 1 is 2, and we change this element to be negative. Of course, in this case, the x we choose can be like int max, it could be something noticeably greater than n, but it has to be positive. So we have seen the element on position 2, so we mark it as negative. Then we have a 4, 4 minus 1 is 3, we mark this one as negative. Then we see this one, the absolute value here is our x, so we skip it. Then we see this 1, it's actually -1 right now, so we take the absolute value, it's 1, points to element, -1 points to element 0, so we give a negative sign to this 3. Then we see another time a 4, points to element 3, it's already negative, we don't do anything, and we skip the x. So after our pre-processing, those elements are still the same. And now, the answer is simply the first position in this array that is not negative. So in this case, the answer is not 1, because here we have a negative sign, so we have already seen a 1 in our original array, but we don't have a negative sign here, and so the answer is 2, which is the first missing integer in our array. And then I'll also show you a second way. In that case, let's first consider what would happen if we were to encounter an element that is pointing to some cell in our array, and if we were to swap this element with the element currently on the place that it's pointing at. So for instance, if we see a 3 here, we look at what's at position 2, and we swap these elements. Well, first of all, if there is already a 3 here, then we shouldn't do anything, especially since if we're doing it in something like a while loop, then we would have an infinite loop. But if it's not a 3, after that swap, we're going to get a -1 here and a 3 here. And what we can see is that 3 is on the position equal to, of course, it -1. So it's in a way in a correct position. Same thing here. We have a 4. We see what's on position 4 - 1 equals 3. It's a 1, so we swap it. In that case, 4 is on its position. So if we are able to ensure that we have done these swaps in such a way that as many numbers as possible are on their positions, then the first position that does not have its proper number is the answer. And I propose that the way to do this is to simply go, let's say, left to right, swap for as long as possible, so swap until the number on our current position is the correct number, and then just go to the next position. Let's see this algorithm in action. First things first, we have a 3 here, -1 on its position, so we swap them, -1 and 3. Then we have a -1, we cannot swap it with anything since it's not pointing into our array, so we go to the next step. So still here we have a 4, a 1, a 4, and an 18. Then we see this one. 4 is not equal to 2, as it should be, so we swap it with element on position 3. 1 here, 4 here. Now this one is not on its correct position, it should be at position 0, so we swap them. So now here we have a 1, here we have a -1. We have a -1, we cannot do anything, so we go to the next position. So right now we have 1, -1, 3, 4, 4, 18. Notice that since we're swapping, we have still 2 4s, 1 18, 1 -1, and 3. So the next position we have here. Now we have a 3, it's on position 2, so it's okay, we go further. We have 4, it's on position 4, we don't have to do anything. We have a 4, it's not on its correct position, but if we were to swap it with the element on its correct position, position number 3, well, it's equal, so we wouldn't do anything, so we can go further. We have an 18, it's not in our array, so we have to skip it, and we're done. And now, of course, notice what happened. The first position that does not have its corresponding number is our answer. So it's position 1, 1 plus 1 is equal to 2, so 2 is the correct answer. And now finally, let's see both of these algorithms in action. Well, let's see their codes at least. Okay, so first on the left we have the second solution, which is the solution that swaps elements and then sees the first position that is not correct. So in order to swap elements, which we're going to do as long as possible for each position from 0, 1, 2, and so on, you have to have 2 conditions to be satisfied. It has to be, let's say, in bounds, and it also has to be in the wrong place. So for checking in bounds, we just have to check if it's a possible answer, not counting n plus 1, because n plus 1 is also a possible answer, but it doesn't point to our array. So it has to be greater than 0, it also has to be less or equal than n, so that nums of I minus 1 is a proper index into our n element array. And then wrong place is just we take the index that it's pointing to, assuming of course it's already in bounds, and we check if the number there is not equal to our current number. Because if they were equal, that would mean that the number on that position is already correct. And if we didn't have this check, then this would be, in this formulation, an infinite loop. And then after these swaps, we just go over every position. So for 0, the answer would be 1. For 1, the answer would be 2, but only if the number is not actually there already. And of course, if everything is fine, that means the answer is the next positive integer. And for the second solution, the one which marks elements, we just first have to pre-process them in such a way that we mark every element that is not a possible answer with something, let's say, greater, something positive, so that we can also mark it as negative later and we won't have any problems. And then we skip all those elements, so elements that are not valid pointers to our array. And for those that are, we make sure that the element is negative on that position. Of course, we have to do it only once, since else if we had two elements pointing to the same position, then we would swap its sign twice. That would not be correct, because we would then say that it was not marked. And then finally, a marked element is an element that is negative. So any element that is positive, we don't have zeros, we got rid of them here. So any positive element is the first unmarked element, so it's the answer. And of course, if everything is fine, the answer is n+1.